Weird. Okay, people at home, let me know that you can hear me because it looks like they have changed some of the settings and the camera is not on.
I can hear you.
Great, thanks. Is Diana Wynn here? Not yet, no. Well, okay, let's get going. So we're a little light on attendance here in class, but that's okay. So last time, oh, actually, before I start this, I thought that was somebody at home. That's okay. I'm trying to close out lab 1. So if you have not turned in a lab 1, please do that promptly. I've already emailed the people in section 1 on Wednesday who've not turned one in yet. And if you have not, please do so. I will be emailing the people in section 2 who've not turned in a lab yet. I want to get that out of the way so we can start to focus on the things that we are trying to do now. All right, so last time we took a look at how competition works in nature, what we see when we see what we believe are competing species in nature, and what the heritage of competition in the past appears to be. which is the divergence of niches. Okay, and it's either temporary, that is, in ecological time, two species can compete for the same resources and each may exclude another from a part of its fundamental niche so that the realized niche is smaller. Or if it goes on long enough in evolutionary time, you may wind up with just different niches. So today we're going to talk about the first part of that, competition in ecological time, and how species that have overlap might behave. So in order to do that, we're going to use the logistic equation, and we're going to add a little term to incorporate the effect of interspecific competition. Now, if you think about what the logistic equation looks like now, it includes that term k minus n over k. And the assumption is that the n that we're talking about is individuals of your species. But that could also be individuals of another species. So k could be affected by the number of individuals of your species as well as the number of individuals of another species. And we'll show you how we incorporate that so that we can model competition. So basically, we will wind up with a large equation, a little bit bigger than the logistic equation, and nobody likes equations, and least of all ecologists. So we tend to use graphs so that we can easily visualize what those equations tell us. But now we're going to focus on developing the relationship between this equation that we're developing and the graphs that we derive from it. So at the end, what we want you to be able to do is to look at the graph and say, okay, that means this in terms of the equation. And we want you to be able to look at the equation and say, if I were to convert that to a graph, this is what it would look like. So the bottom line is that competition has 4 different outcomes, and we'll show you how they work. And there is something called a competition coefficient, which is pretty important, and we'll show you how we derive that. Because just because you have a member of another species does not mean it will have the same effect as a member of your species. Might have a greater effect, might have a lower effect. And then finally, we'll look at the assumptions of this little model we are developing and how the real world is often more complicated than that. How we have to be mentally nimble to apply this. So first let me get my advance. There we go. So what is the effect of competition between species on the carrying capacity? Well, the presence of a competing species should reduce the carrying capacity because they're using some of the resources that your species wants to use, needs to use. So if there is another species using some of your resources, your carrying capacity is going to be reduced. So for every individual of another species that is in competition with you, your carrying capacity is going to be reduced by a small amount. Okay. Now, the amount by which a single competitor reduces carrying capacity is called the competition coefficient. And we usually, I'm going to move this back up now, we usually symbolize that by either alpha or beta. Right, and we'll talk about this a little more in a minute. But the important thing to understand is that if a competing species holds a big territory, it might reduce your carrying capacity by the equivalent of more than one of your species. It might use enough resources or prevent you from using enough resources so that your carrying capacity is reduced by 2 or 3. So the competition coefficient can vary. It can be greater than 1. If it's 1, then the effect of another species on your carrying capacity is equal to adding another individual of your species. But now remember what we talked about when we talked about the niche and niche overlap? We made the point that in a lot of cases, species do not share identical niches. They may share only a portion of their niches. And in that case, a member of a competing species might have only half the effect on your carrying capacity that one of your species does, because it's not using the same set of resources. And we have a question in class. Dwayne. Okay, so Dwayne is saying, do we assume that species that are sharing niches are not trying to kill each other? Yeah, competition is much more subtle than that. Basically, it's you grabbing resources and causing the other species to go hungry. They're not killing each other, usually. Not usually, anyway. Although that does happen, but it's not the typical case. All right, so in this graph, what we're showing you is we're adding one individual of a competing species, and we're reducing the carrying capacity by this amount. The amount by which we're reducing carrying capacity is the competition coefficient. And we're either going to call it alpha or beta. And remember that if we have two species competing, then species A will reduce the carrying capacity of species B. Species B will reduce the carrying capacity of species A. So we're actually going to have two versions of the logistic equation, one for species A and one for species B. And each of those versions will have a competition coefficient that quantifies the effect of one species on the other. So where do we go from here? We'll go down to the bottom so we can advance. I don't know why it's doing that. All right, so here's our normal logistic equation, and I'm going to write it K minus N over K. But now, if we're going to talk about having two species in competition, we have to specify which species we're talking about. So now we're going to talk about dN1 dt. That's the change in the population size of species 1 over time. And of course, it would equal then the exponential growth rate of species 1, R sub 1, times the number of individuals of species 1, that's N1. So here's our familiar dN dt. And then here's the logistic part, right? And so now we're going to specify that it's the carrying capacity of species 1 minus the number of species 1 in the population currently divided by the carrying capacity. That's what the logistic looks like when we start thinking about it in terms of having to track two different species. We need to specify which one we're talking about. But if we want to model inter-specific interactions, excuse me, we need to know how many individuals of species 2 are present, and we need to know what the effect of each individual is on K of species 1. So that's down here. I don't know what's, I guess I'm going to cough for a while. It's right here. So this term here, alpha times N2, specifies the effect of species 2 on the carrying capacity of species 1. Okay, so for every individual of species 2 that is present, you reduce the carrying capacity of your competitor by the amount alpha. And that could be a really small amount if their niches don't overlap. You know, it could be like 0.1, could be 0.05 if they're not sharing a lot of resources. Or it could be greater than 1. And we have another question from Dwayne. It's what? It specifies the interspecific effect of species 2 on the carrying capacity of species 1. So now this equation has an intra-specific part, and that's K1 minus N1 divided by K1. But it also now has an interspecific term, which is alpha times N2. Okay, and I see that Jason has a question, yes? It is not going to always be a number less than 1. Most of the time in the problems that I give you, it will, but not always. Okay, no. Remember what's going on here. This is a minus sign. This is a, where's my cursor go? This is a minus sign down here. So what we're saying is that if it's greater than 1, then K1 will be reduced by a relatively large number because you're multiplying the number of the competing species by a number greater than 1. Okay? So this is a minus sign. This is how much K is reduced by the other species. All right, so there's an equivalent equation for species 2. And what we typically write is dn2 dt equals r sub 2 times n sub 2 times the term k of species 2 minus n of species 2, and that's just the logistic part, minus the extra effect of species 1 on species 2, which would be beta n1. So beta is the effect of 1 on 2. Alpha is the effect of 2 on 1. Now, graphing the results of these equations will help us understand how competition actually works. So what do we focus on? Well, let's focus on carrying capacity. Let's focus on the point at which the population stops growing, which is carrying capacity, right? So for species 1, if there are no members of any other competing species, then species 1 population will stop growing at its carrying capacity, K1. But what happens if you add a competitor? If you add a competitor up here, then you're going to have the y-axis be up here, not at the bottom here. It'll be a little bit up. What happens to K1 if you do add that? Well, you're going to reduce the effective carrying capacity of species 1 by a little bit. It's going to be less than its nominal carrying capacity because this one competitor of species 2 is now using some of the resources. What happens if you add another competitor of species 2? Well, I think you can see we're getting a trend here. As you add individuals of a competing species on the y-axis, the point at which the species 1 population stops growing tends to drop below carrying capacity progressively. And the more that you add on the y-axis, the smaller the number of species 1 you'll be able to support indefinitely, because species 2 is using more and more of species 1's resources. So if you just keep adding species 2, the competitor, now you have 3 competitors and it's doing the same thing. So what's the logical conclusion here? There will be what we call a zero growth isocline on this graph that tells you the combination of species 1 and species 2 individuals that forces species 1 to stop growing. If there are 0 species 1 or species 2, then 0 growth occurs at carrying capacity. But if you start adding competitors, species 1 will have to stop growing at smaller and smaller densities. And eventually, you'll have so many of the competing species that there will be no resources left over for species 1 at all. Species 1 will go extinct, and you'll only have whatever this number is of species 2. So species 2 could use all the resources and not leave anything left over for species 1. So you'd have whatever this number is of species 2 and 0 species 1. Okay, so we have a negative slope to this 0 growth isocline. Everywhere on the line, the population does not grow. Everywhere below the line, there's enough resources for species 1's population to grow. So it can grow from 0 all the way out to this line, at which point it will have to stop. Up here, if you have this many of species 2, then species 1 can grow all the way to this point, and then it will have to stop growing. What happens if you get more individuals of species 1 than the line indicates? Well, then you're out here. You are above your carrying capacity. Species 1's population will have to decline. It'll have to go back towards the axis. So species 1 is growing from left to right, and it is declining from right to left. If it hits the line, it stops and is stable. So the line tells you what combination of species 1 and species 2 causes species 1 to have a stable population. It could be this combination of species 1 and this number of species 2. It could be this number of species 1 and that number of species 2. Whatever it is, the two species are using all of the resources available. All right, well, that's good. We have one of our two species, but we have two species. So what happens if we graph the isoclines for the two species on a single graph? Hey, we could get something that looks like this. So here you'd have the isoclines for both competing species. And this is really interesting because the position of these two isoclines tells you what's going to happen in competition. This will tell you whether one species causes the extinction of the other or whether they can coexist. So here we have the four cases. So in this case on the upper left, the species 1 isocline lies outside the species 2 isocline. So they put the carrying capacity for species 1 here. They didn't bother putting the carrying capacity for species 2 here. I should really get a better graph that's better labeled. But this is species 2 isocline, this is species 1 isocline. So let's look at what's happening here. Okay, for species 1, this is the axis for species 1. Okay, so if species 1 is below its isocline, it can grow until it hits that isocline. If it's above the isocline, it must decline back to the left until it hits the line. What about species 2? Well, species 2 is on the y-axis. So species 2 grows this way, and it declines this way. So let's have a look at what's going on in these three sections of the graph that are defined by these lines. Well, down here, you are below the species 1 and species 2 isoclines. Species 1 can grow this way. Species 2 can grow this way. Okay, but at some point, you're going to hit this species 2 isocline. When you hit the species 2 isocline, what happens? Well, nothing happens to species one because it's below its isocline. It can keep growing. So it can continue to grow here. But now species one is above its isocline. There are too many individuals for the environment to support, and species two must decline. So you're going to go this way and this way. And the net movement in this center space is going to be in this direction. Okay, well, what happens if you go too far in this direction? Well, species two is continuously declining, and species one is continuously increasing. So for every individual of species two that dies off, species one takes the resources. And eventually you hit the axis. And what density is this of species two? 0. And species one is at its carrying capacity. So in this case, the species one isocline lies on the outside of the species two isocline. Species one drives species two extinct. All right, and we know that we have to have this as a possibility if we're going to have a realistic understanding of biology. What happens if the isoclines are reversed and the species two isocline lies outside the species one isocline? Well, okay, so here's species one's isocline now, and here's species two's isocline. So remember, species one grows from right to left, or from left to right rather, and it declines from right to left. Grows left to right, declines right to left until it hits this line. Species two grows up and declines down until it hits this isocline. So again, in this little triangle near the origin, both of the species are below their isoclines and both of them can grow. So we're only showing you species two growing because that's going to be the eventual winner, but actually a point in this section will move actually at a 45-degree angle because both species are able to grow. So two grows this way, one grows this way, and a point, any combination of the two species in this triangle will go that way at a 45-degree angle up until it hits the species one isocline. When it hits the species one isocline, you now have too many individuals of species one, and some of them have to die. So species one, if it gets in this area, has to decline. But every time an individual of species one declines, notice that species two is still below its isocline, and it can still grow. So they take the resources that species one is giving up. So species one grows in this direction. Species two grows in this direction. Species one declines in this direction. And the net movement is in this direction. And eventually, what will happen? You'll get species two going to its carrying capacity, and there will be 0 species one. So when the species two isocline lies outside the species one isocline, species two is the winner. Species two drives species one extinct. Okay, I'm always going to label the points at the ends of the isoclines, unlike this one, which is slightly confusing for that part. But this is always going to be K2. This is always going to be K1. We're going to leave this axis, this point here undefined for the moment, and this one undefined for the moment. But I'll show you how to find them. But okay, what we can do with these two top graphs then is model a situation in which one species drives the other extinct. Just look at which isocline lies outside the other. If the carrying capacity for species one is out here, that means that this is the species one isocline. If the species 2 isocline is entirely inside it, species 1 drives species 2 extinct. End of story. Look for the K for species 2. If it is here, this is the species 2 isocline. And if species 1's isocline lies entirely within species 2 isocline, then species 2 will drive species 1 extinct. But we have a problem, right? Because we know that species coexist. And so far, these top two graphs don't let us do that. Well, we're going to have a negative slope to our isoclines, right? But who says they can't cross? Who says the slopes can't be different? We've drawn these with equal slopes, but what if the slopes differ and the lines cross at some point? Oh, okay, well, that's a very different situation. So down here on the lower left, you have a situation where the species 2 isocline starts on the outside of the species 1 isocline. So the carrying capacity of species 2 is greater than the end point for the species 1 isocline. And similarly, the species 1 carrying capacity here is greater than the end point of the species 2 isocline. Well, what happens? Well, once again, if you are in this little not quite triangular space here near the origin, both species can grow. Species 1 can grow from left to right. Species 2 can grow from up bottom to top. When you're out here, both species must decline because both species are above their carrying capacities in this entire area. So species 1 has to decline from right to left. Species 2 has to decline from top to bottom. But what happens in the little triangles? That's interesting. Well, notice that when the lines cross right here, you have an equilibrium. You have a stable point. This combination of species 1 and species 2 will stay at that point unless it moves away, either to the top right, the bottom left, or top left and bottom right. If it moves away from this point, it might not come back. So this is an unstable equilibrium. How does it work? If the combination of species gets into this triangle here on the upper left, then look what happens. You're below the species 2 isocline, so species 2 can increase, but you're above the species 1 isocline, so it has to decrease. If you move away from this unstable equilibrium into this space, species 2 will drive species 1 extinct. Apologize for that. If you move into this triangle down here, then you are below the species 1 isocline, and species 1 can increase from left to right. But you're above the species 2 isocline, and species 2 must decrease. So you move this way, and species 1 causes the extinction of species 2. So we have a situation in which we can have an unstable interaction. They can be at an equilibrium, and as long as they are at that equilibrium, they can coexist. But if anything happens to give one species or the other a little bit of an advantage, if you move the combination of the two species away from this equilibrium point, then it's quite possible for species 2 to drive 1 extinct, or for species 1 to drive 2 extinct. The final case is where these carrying capacities are on the inside. So here you have the carrying capacity for species 2 be greater than the endpoint of species 1. Here, species 2's carrying capacity is less than the endpoint for species 1. And here, the carrying capacity for species 1 is less than the endpoint for species 2. So it's the opposite situation. This carrying capacity here is now down here. This carrying capacity here is now in here. All right, well, you again have an equilibrium because the lines cross, and this number of species 1 and 2 will be stable. But what happens if you move that combination away from this equilibrium? If you move it down here, both species will grow. If you move it up here, both species will decline. If you move it to the upper left, you are now below the species 1 isocline. Or you're now, I'm sorry, this is now, yeah, this is the species 1 isocline. So you're now below it, and you can grow. You can grow from left to right, but you are above the species 2 isocline. And so in this little triangle, species 2 declines, species 1 increases. And any combination of the two species in this triangle will move right back to the equilibrium. If you move into this triangle on the bottom right, then you are above the species 1 isocline now, and species 1 must decline. It has to move from right to left, but you're below the species 2 isocline. So species 2 can increase. Any combination of the two species in this little triangle will move up and to the left, right back to the equilibrium. So in this case, it's a stable equilibrium. If you can think of another outcome we need to model, please let me know, because that's all I can think of. Species 1 can drive species 2 extinct. Species 2 can drive species 1 extinct. They could coexist kind of unstably, or they could coexist stably forever. That's a pretty good solution to modeling what we see in nature. We've accounted for all of the cases that we actually see in nature. We can have coexistence. We can have competitive exclusion. That coexistence can be stable over the long term. It could be unstable. And we see all of those. So this translation of the two equations onto a graph is actually extremely helpful. I will want you to be able to tell me what the movement of any combination of species 1 and species 2 might be. If it's out here, they're going to go this way. If it's in here, they're going to go this way. But if it's in the middle here, they're going to go that way. So you're going to have some problems to practice on. Now, we haven't yet talked about how you calculate those coefficients, the competition coefficients, alpha and beta. And you actually can do that if you do a competition experiment. Because remember, Georgie Gauss had the experiment where he grew his microorganisms to their carrying capacity, and then he added another species, and he looked at what happened to the carrying capacity. Well, we can do that. And we can say, all right, if you add 10 individuals of this species, how much does the carrying capacity drop? Well, if you lose 5 individuals of your target species and you've added 10 competitors, then each of the 10 competitors has half the effect on K than an individual of your target species would. So you just take the reduction in numbers and divide it by the number of competitors that cause the reduction. And that gives you either alpha or beta. So here's an example. So we've got a little species that has a carrying capacity of 100, and let's say it's in a Let's say it's in a test tube. If we add 50 competitors of a different species, let's say the number drops from 100 down to 80. So adding this number of individuals of species 2 caused K to drop by 20 individuals. So what's the average effect of each competitor? Well, the total difference is 20, and it took 50 competitors to cause that reduction. So 20 divided by 50 gives you a competition coefficient of 0.4. It's as simple as that. It's actually much more complicated to do the experiment because a lot of times you have species that are capable of causing the extinction of the other. So you have to monitor it very carefully. And these experiments are not, in fact, as easy to do as I suggest. But this is how you'd write the equation for species 1 then. dn1 dt would equal r1 times n1 times our logistic factor, which is k1 minus n1 minus 0.4 n2 divided by k1. Because each individual of species 2 has 40% of the effect on k that an individual of species 1 has. So this is something that we can derive from observation. We add a competitor of some known number and we ask, how many of our target species have to die off to reach stability? We divide that number by the number of competitors we added, and that's the average effect of each competitor. End of story. Okay, so here's a sample problem. So here you've got K1 at 100 when there's no competition, and for species 2, K is 50. If you add these two together and let them come to stability, you find that you can maintain 75 of species 1 and 25 of species 2 in the same experimental arena, whatever, test tube, something. All right, well, so look, alpha is the effect of species 2 on species 1. What did species do to the carrying capacity of species 1? It reduced it by 25. 25 individuals caused that reduction. So alpha is 1 because each individual of species 2 has exactly the same effect on K1 that an individual species 1 has. So alpha is 1, 25, which is the difference here, divided by 25, the number that caused that difference. What about K2, species 2? What about beta, the effect of species 1 on species 2? Well, K2 dropped from 50 to 25, so the difference is 25. How many individuals of species 1 caused that? 75. So beta is 75, is based on 75 competitors. And beta is 25, the difference here, divided by 75, the number of competitors that caused the difference, is 0.33. So you can calculate these competition coefficients, and you will do that in a practice problem. Now, I said that we have left the endpoints, the opposite ends from the carrying capacities, undefined initially. But now we want to put a number on them, right? So here we know that this is carrying capacity of species 1, and there are 0 individuals of species 2. But how many individuals of species 2 would it take to use up all the resources that species 1 would normally use? We haven't actually got a number for that yet. But now we're going to show you how to get it. So look, at this point, notice that our term for reducing K in the logistic equation, the modified logistic equation, is now K1 minus N1 minus 0, because there are 0 individuals of species 2. So logically, what you'd want to do is ask, well, okay, at this point, how many individuals of species 1 are there? 0. How many individuals of species 2 are there? Ah, that's the problem. So this is the species 1 equation. N1 would equal 0 at this point. So K1 minus 0 minus alpha N2 would be what's left in this term. So if all of the resources are used up, then K1 would equal alpha N2. There you go, K1 equals alpha N2. This number of species 2 uses all the resources that species 1 would use. So K1 would equal that number, adjusted by the effect of each individual. So now you have an equation. And N2 would equal K1 divided by the effect, alpha. So it's K1 divided by alpha. That's the endpoint of the isocline. For the species 2 isocline, it's the same thing. It would be K2 divided by beta, the effect of species 1 on species 2. So now if you know the numbers, you can draw the graphs. Yes? Because right here on this axis, there are 0 individuals of species 1. There's only individuals of species 2. Okay? So all we're doing is saying at carrying capacity, there are 0 competitors. But at this point, there's 0 individuals of species 1, and only species 2 is present. So we can solve for that number. N2 would equal K1 divided by alpha. Okay, so when we do these analyses, what do we get? Can we actually use them? Do people actually use them? Oh, the answer is yes, absolutely. We do use them. And here's a great example. So here is the isocline set for 2 species of mosquitoes, Aedes albopictus and Aedes triceriatus. And this is in Florida, so it's kind of trashy. But albopictus is the tiger mosquito introduced from Southeast Asia. It is a serious vector of dengue fever. And of course, the CDC is very concerned about dengue fever because it's a very serious disease. Aedes triceriatus is a native species. It's a tree hole nester. So they look for water that is caught in, say, the place where 2 branches of a tree might diverge, and there's a little hole there. That's their natural breeding habitat. But then again, it being Florida, there's a lot of discarded tires laying around Florida. Just people unload their old tires off the back of their truck and just throw them out in the swamp. So there's more than one place for these mosquitoes to breed. Now, on the left, you see the interaction between triceriatus and albopictus in tree holes. Notice that there's a stable equilibrium here. So they do coexist, but albopictus cannot achieve really high densities because triceriatus is able to coexist with it and use some of the resources. So if they're only using tree holes, you'll have relatively low densities of this vector of dengue fever. In discarded tires, though, here's the isoclines. Notice that the albopictus isocline lies entirely outside the triceriatus isocline. So in this case, what happens if one isocline is completely outside the other? The one that's outside drives the one inside extinct. So albopictus can monopolize these these discarded tires, and they can achieve much higher densities than if they were nesting in tree holes. So this has a couple of object lessons. Number one, don't dump trash because you may get dengue fever. Albopictus is present in Louisiana too, not in as large numbers, but we do have cases of dengue fever that are transmitted by albopictus. So, and this competition is context dependent. Yes, we have a question in class.
So are they coming larvae?
These are larvae, yes, these are larvae. Yeah, because of course mosquitoes, adult mosquitoes that fly don't live in water. I mean, these are the larvae that are developing in the tree holes or in the spare tires. Okay, so let's see if we can get through this. We've been really good about getting through the presentations, but I'll end with this. There are three assumptions that must be true for using the competition coefficients to predict the outcome of competition. First, they have to be constant as density changes. Second, they have to be constant for a particular interaction, and the environment should not affect them. And third, and most important for our extending this to think about communities, they should be constant when you add other species to the mix. Okay, well, we know that these three things hold in some cases, but they don't always hold. So it may be much more complicated to apply this in the real world than we've just presented. So let's quickly run through an example. Here's an example of nonlinear competition. So here are two fruit flies. We'd predict from the numbers here that they would have an equilibrium right here at this combination, somewhere around a little over 300 pseudo-obscura and somewhere around maybe 700 serrata. In fact, this is where the equilibrium occurs. And it occurs because there's a change in the value of the competition coefficient as density changes. If you add one individual of serrata, it causes a big drop in the number of pseudo-obscura, and vice versa. Okay, so the initial individuals have more of an effect on K than other individuals that you might add later. So non-linearity is a problem. Second, alpha and beta can vary depending on the environmental conditions. And this shouldn't be terribly surprising, but what's actually kind of surprising is the number of times where we don't have to worry about this. But here's an example using flower beetles. So we have two species of flower beetles, and we have three temperatures and two humidities. And look at the percent of contests won by the two species. In cool, dry conditions, Tribolium confusum is the clear winner. But in warm, moist conditions, Castanium is the clear winner. Well, clearly, the competition coefficients vary with temperature and humidity. Oh dear. So this is a more complicated interaction to model than the simple ones we've been talking about. Okay, finally, if we add other species, those values can change dramatically. So here we've got two conditions. We've got four different little microcrustaceans. Okay, and we've got high allele present and then high allele absent. So you see some here and none here. Well, the interaction between the other three should be constant regardless of whether high allele is present or absent. Is it? Well, let's do the calculations. Let's not look at these numbers. Let's do the calculations. So with high allele, the effect of C on A is 0.67. Without it, it's 1.47. Oh, crap. The effect of S cymocephala on allanella is 0.37 when high allele is present. And it's actually a positive because remember, we're subtracting this times N2. So this is actually mutualism. It benefits allanella to have these guys when without high allele, but it hurts them to have them when high allele is present. Again, all of them are really interesting. There's only one that doesn't really change, and that's this one here. So the take-home message here, because the coefficients are not constant, you have to be very careful trying to generalize from a two-species interaction to what might go on in a particular community. The particular community's composition prevents us from making these predictions with high confidence. Okay? Now, you're going to get some practice problems. You're going to practice drawing a graph from an equation, sort of figuring out what the equation should look like from the graph. You're going to get some practice calculating the competition coefficients and using them to draw those graphs. It'll be loads of fun. Okay? Anthony, I have a lab report. And did Diana Wynn come in person today? I have a lab report for her too. Okay. Okay, well, Diana, next time you show up, you'll collect your lab report. All right, next time we will talk about the evolutionary responses to competition. And do we have any questions from home? Okay, guys, I'm gonna log you all out. I'm gonna run to City Park and get some pond water.